Assalamualaikum warahmatullahi wabarakatuh. I'm Balkis Asha binti Muhammad Zawawi, representative from the Group 1 for this project. Before we get into our design, let's quickly cover the basics one. Bridge help us cross obstacles like rivers or roads. Their design depends on factors like location, materials, and cost. For this project, we focus on Truss bridge. This bridge uses a network of triangle to carry loads efficiently. Here the simple rule. The top members are pushed together. This is called compression. The bottom members are pulled apart. This is called tension. The diagonal and vertical members can experience either one depending on the load. In short, truss bridges are strong, light and cost effective, which makes them ideal for long spans. That's why we choose them for our project. Our project was driven by three main objectives. First, our primary goal was to evaluate the stability of bridge design and determine their capacity to support a specified load. We needed to ensure that our design could withstand the forces it will encounter in a real-world scenario. Second, we aim to build the lightest possible bridge that could span a set distance. This is a crucial aspect of engineering, as reducing weight, minimize material costs, and makes construction easier, all while maintaining the safety standards outlined in the project requirements. Finally, we strive to develop an innovative and constructible model bridge. We didn't just want to design something on paper, we wanted a model that could be a physical proof, demonstrating a creative yet practical approach to bridge engineering. So, our problem statement is how to do the bridge layout and design based on existing bridge. Our task was to analyze an existing bridge design and create detailed layout. Its main understanding its geometry, member connections, and overall form to replicate and improve upon it for our model. Second, what is the support reaction of each member of the truss bridge? This is where the structural analysis begins. We needed to determine the forces, specifically the support reactions, experienced at the supports and within each individual member of the truss. This is critical to ensure every part is strong enough. And the last one is which is method is suitable for calculating the internal force and the deflection. To find those internal forces and predict how much the bridge will bend or deflect under load, we had to select the most appropriate analysis method. This involves deciding between techniques like the method of joints method, of sections, or using computational tools or more detailed analysis.
So now that we have established our project background and objectives to build a highly optimized 800 mm span bridge, let us move on to the slide 3 to look at the underlying structural physics of our chosen configuration, the whole truss. So for the first one, at the heart of the whole truss configuration is how it handles structural forces. Traditional solid beams suffer from severe internal bending stresses when loaded. The truss, however, bypass this limitation. By utilizing pin-connected members, it translates external vertical loads strictly into pure axial forces, meaning our basalt elements experience either pure tension or pure compression. So what makes the home layout unique is its specific arrangement. Under gravity loading, the diagonal members are placed in compression while the vertical members carry tension. This predictable load path is exactly what we aim to analyze. Of course, managing these forces requires extreme structural stiffness. The whole truss achieves this through its interconnected network of rigid triangular units. Since triangles are geometrically undeformable, they provide the necessary stability to prevent local buckling failures. This geometry allowed us to use extremely light 5 mm by 5 mm balsa wood members to bridge a massive span, achieving an exceptional strength to weight ratio that is highly sought after in bridge engineering. Finally, from an academic standpoint, we choose the whole design because of its static determinacy. By satisfying the determinacy equation, which is m plus r equals to 2 times j, where m represents the number of members, r represents the support reaction forces, and j represents the joints, we can mathematically prove that this structure is statically determinate. This means we don't have to guess or rely solely on software. We can precisely verify every single internal member force using traditional hand calculation, anchoring our FEA simulation in core provable physics. With these fundamental physical principles verified, let us look at how we translated this math equation into actual physical dimensions, material properties, and costs in slide 4.
Okay, so next, the item that we use in our construction is balsa wood, hot glue gun, super glue, and also the sewing thread. So the total cost of this item is almost 74 ringgit. Okay, why you choose balsa wood? Because it is lightweight, easy to cut, and also as simple to assemble. Other than the weight is light, it can still demonstrate the structural behavior of a real truss during the testing. So for joint reinforcement, the joint were strengthened using a combination of super glue and also hot glue gun and also the quarter wrap. This method can help to make the connection more stronger and more rigid by reducing the change of the joint breaking or rotating when the load is applied. Next, I will explain about the engineering methodology that we use in our project. So the first, we select the whole truss configuration based on the information from the previous study and also the engineering references. We also calculate the basic geometry, including the span length, panel dimension, and also the member arrangement to ensure the design meet the project requirement. So after that, the truss was modeled using the Step Pro software. The balsa wood material property were assigned and the support condition were defined to simulate the actual behavior of the structure under loading. So next, the physical model was constructed using the balsa wood. Each member was carefully measured, cut, and also assembled. The joint were reinforced using super glue and also hot glue gun. And next, we wrap with the cotton thread to improve the strength and stability. So for testing and analysis, the load was applied at the midspan of the truss bridge. The structural response and deflection were recorded and compared with the analytic and software result to evaluate the accuracy and performance of the design. So this workflow ensured that the truss bridge was designed, analyzed, and fabricated systematically so that which is allow us to assess its structural behavior effectively.
Next, I will explain the finite element analysis that we carried out using Step Pro. We developed a three-dimensional space frame model consisting of 36 joint and 67 structural elements. This model accurately represents the stiffness and behavior of the truss bridge when subjected to loading. From the analysis, we observe the expected distribution of axial force. The upper cord member are mainly under compression, while the lower cord member carry tension. This confirms that our whole truss behave according to structural theory. For the support condition, we assign a pin support at the left and a roller support at the right end. This boundary condition simulate the actual bridge support and allow the structure to expand or contract without generating unnecessary stresses. Overall, the Step Pro analysis help us evaluate the structural response, verify the internal forces distribution, and ensure that the bridge design is stable and safe under static loading. After completing the computer analysis, we verify the result using a manual calculation based on the principle of virtual work. In this method, we apply a unit virtual load at joint E, which is located at midspan of the bridge. We then calculated the contribution of every member using the virtual work equation to determine the maximum deflection. In the formula, N represents the virtual force, capital N is the actual force, L is the member length, A is the cross-sectional area of 25 square millimeter, and E is the modulus elasticity of balsa wood, which is 3.5 gigapascal. The calculated maximum theoretical deflection is 1.99 millimeter. The small deflection indicates that the bridge has good stiffness and can resist deformation under the applied load. By comparing the manual calculation with the StatPro result, we confirm that our structural model is accurate and that the bridge design satisfies the required engineering principle.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fatimah binti Zubair. My matrix number is BFC21403. In our project, we have successfully fabricated an 800 mm whole truss, which has 700 mm effective span with pin and roller supports, placed 50 mm from ends, designed to support a 400 central mid-span point load. We also use StatPro 2025 to generate an accurate structural model, accurate precise calculations for support reactions, internal action forces, and nodal displacements. In conclusion, we have achieved structural design reliability by verifying that physical behavior and computer outputs align perfectly with manual structural analysis calculations before construction. However, there is a few recommendations on improvement on our project. The first one is joint reinforcement, which we have to attach thin plastic cassette plates to critical nodes rather than relying solely on glue and thread, distributing stresses evenly and preventing typical joint rupture failures. Secondly, we also need to avoid using uniform 5x5 mm square balsa wood vary member thickness according to compressive load levels to increase buckling resistance. The last one is we need to conduct destructive and non-destructive weight loading tests to determine the actual strength to weight ratio and confirm theoretical capacity limits.